In this lesson, we're going to define something called the dot product. And we need the dot product to do some other calculations with vectors. So the dot product is an operation with two vectors. So if I'm given vector u is u1 and u2, and vector v is v1 and v2, then we're going to define the dot product like this. U dot, which is a solid circle, a solid dot, v. The dot product is going to be the answer you get when you multiply u1 times v1 plus u2 times v2. And this kind of looks like what we did with matrices, where we multiplied matrices. Only this is much easier because we're just multiplying corresponding terms and then adding them together. Well, what we get when we get done is a scalar. We get a single number out of it. It's like the inner product with matrices. It yields a scalar. So the dot product takes two vectors and creates a scalar as an answer, not a vector. Alright, I have a couple vectors. U is -1, 3, and v is 5, -2. I'm going to find u dot v and v dot u. So u dot v, that's what you get when you take -1 times 5 plus 3 times -2. So -5 plus -6. Looks like that's going to be -11. Well, v dot u, let's see what this is. V dot u is the same thing, really. It's going to be 5 times -1 plus -2 times 3. So -5 plus -6, and it's -11. What that means is that the dot product is commutative. U dot v is going to be equal to v dot u. And we can show that generically because if I have u and v here, and it works for any number, I can say u dot v is u1 v1 plus u2 v2. V dot u is v1 u1 plus v2 u2. And they're basically going to be the same because of the commutative property. So that's going to be true. Now we're going to talk about some properties of the dot product. So we'll start off just saying we're going to let u, v, and w be vectors in the plane. And actually we don't talk about in space this year, but it really doesn't matter. And c is going to be a scalar, meaning just a plain number, and it's not a vector. So the first property is what we just showed, is that u dot v is equal to v dot u. So the dot product is commutative. The second property is the fact that the dot product is distributive. So u dot the quantity v plus w is the same as u dot v plus u dot w. So you can distribute the dot product just like you could distribute a coefficient in front of a binomial. The next property is the fact that I can multiply a scalar, and the location or the point of multiplying the scalar doesn't really matter when you do the final dot product. So c, scalar c, times the dot product of u and v. I could also, that's the same as multiplying u by c and then taking its dot product, or multiplying v by c and then taking the dot product. So a scalar can be applied at any point. Alright, the next property is if I have the zero vector. The zero vector would be have an x and y components both of 0, and I dot that with any other vector, I'm going to get 0 as a scalar. Finally, when you take a vector and you take the dot product of a vector to itself, that's equivalent to the magnitude squared. And we can think about how we could prove that. Maybe we'll do that in class. So we'll finish with working a few examples here. If I have these vectors, u is 2, negative 2, v is 5, 8, and w is negative 4, 3, we're going to perform the following operations. The first one is just the dot product, u dot v. So u dot v is going to be 2 times 5, 2 times 5, plus negative 2 times 8. So don't make this complicated. It's really quite easy. So this is 10 plus negative 16, which is negative 6. Remember, when you take the dot product, you get a scalar for an answer. That's not a vector anymore. So part B, we want to u dot v times w. Well, we already have this answer. We know that that's negative 6. We just found it. So we're just basically multiplying negative 6 into the vector 4, 3. I don't even know if I need those extra set of parentheses. That's probably actually, okay, that's going to bother me. Let me do that again. Negative 6 into the vector 4, 3. That's better. Alright, so if I do that, that answer is negative 24, 18. And the next one, I'm going to take the dot product of 2v. Well, I can cheat a little bit and say this is the same as taking the scalar, multiplying 2 by the dot product of u dot v, which I already have, which is negative 6 again. So that just saves me a bunch of work. And that's negative 12. So there's my answers so far. Finally, w squared, that's going to be the same as, or the magnitude squared is going to be the same as taking w and dotting it with itself. Again, it's going to yield a scalar. So if I take vector w, which is negative 4, 3, this is the same as negative 4 times negative 4 plus 3 times 3. So you're basically squaring each term and adding them together, and that gives you 25. And there you have it. We're going to be working more of these in class, but the dot product is a rather simple operation. It's nothing like the inner product for multiplying matrices. It should be pretty straightforward.